That's fine. Yeah, thanks, Ryan, and hello, everyone. I guess to add on to your question and answer, Ryan, if you see anything in the chat during the meeting and presentation, I'm fine with answering it right then and there. If you see anything that's relevant to a specific slide that we talk about, it's up to you if you want to go before or after. But I'll introduce myself. I'm Otto Schwieterman, and I'm a systems engineering manager for Emerson. We make Copeland scroll compressors is who I really focused on. I have application engineering support for several commercial OEMs in the area. Right now, there's been quite a bit of demand for questions about heating with electric, instead of using natural gas, and in some residential cases, propane. For heating, there's been more of a push for heating applications, and scroll compressors is one option to do that. In the past, heating has typically been demanded more in Europe instead of here in North America for being used with compressors. But as we move into a greener solution, we start seeing that need for heating with scroll compressors as well. Yeah, this first slide, it's really going over the different applications that we have and what we target with heating with scroll compressors. You can see the blue areas, kind of your typical cooling conditions that you're typically going to see, and then the big red star is what you're going to see for typical heating applications. The evap temperature is the saturated suction temperature that you've seen on the bottom, and on the left, the vertical is the condensing temperature, which is your saturated discharge temperature. Typically, you have roughly a 10-degree delta T between what your ambient outdoor temperature is and then what the evaporating temperature is going to run at. So let's say it's 0 degrees outside. I mean, it's going to be based on the system design and their coils, but you're going to be, between -10 and -15 degrees evap. And then the same thing with the condenser. If you're trying to make a 130-degree hot water, let's say, you may run between 120 and 120. Or if you're trying to make 120-degree hot water, you may run between 125 and 130-degree condensing. That really depends on the OEM and each system and each one of their coils as well. Some will have a variance in there. But as you can see, this is kind of a general example of what we call a vapor injection operating envelope. You can see some limitations on what that max condensing temperature is, and that's generally going to limit you on what hot water or hot air temperature you can make. Typically, in order to make hot air, you can probably use the typical scroll compressors that there is out there today. Especially variable speed compressors allow you to run at lower evaporating temperatures and higher condensing temperatures that way. But as you'll see in the presentation, there's still benefits of increasing capacity of doing some type of injection with a compressor itself.
Hey Otto, one of the attendees is asking on the chart you just showed, what type of refrigerant is this based on?
Yep. So today, vapor injection is typically used with R410A. In the future, and in Europe, they're using R454B and R32 for vapor injection offerings. They're both high pressure refrigerants, and part of the reason we use high pressure refrigerants is if you start using R134A or low pressure refrigerants that are typically used in like heat recovery chillers, those heat recovery chillers has higher evap temperatures. So if you use a low pressure refrigerant, a lot of times we run into a problem where there's not enough force to keep this floating seal sealed with the muffler plate in the compressor. So you're not actually going to be able to run at what I call high compression ratio conditions, which is the top left. I'll have another slide coming up in here as well to kind of explain that. This is really kind of a more detailed overview of the different heating options that we have today. Like I said, if you're making hot air, typically fixed capacity compressors and variable speed do well for, air side heat pump systems. But if you're wanting to make hot water, some type of injection, it can be vapor injection, wet injection, or liquid injection is really needed in order to really get that hot water temperature up that you need due to the increased condensing temperatures. We do have various compressor offerings below 15 horsepower. I mean, as we know, New York City has it gives you a big benefit of using models that are less than 15 horsepower. So, there are tandem offerings as well. So you can select 2 smaller motors to get under that 15 horsepower requirement.
Otto, can you talk a little bit about what vapor injection means?
Yep, I'm going to go here in the next couple of slides, but really what vapor injection is we're taking some refrigerant from the liquid line, and we are routing it back to the compressor and injecting it right into the scrolls to help keep those scrolls cooler. Because I'll go back up to this next slide. As you start running up on the upper left side of the envelope, which we consider high compression ratio conditions, that increases what that discharge temperature is. Compressors can only handle, a certain level of what a discharge temperature is. So we will want to directly dump that vapor injection, or, a mix of vapor and liquid or pure liquid, into the scrolls in order to cool them so they can operate up in this top left region. And like I just went over, there's really 3 main injection types. Each has their own benefits from each other. Vapor injection is the most efficient option, and the reason for that is you get a capacity increase by bringing that vapor refrigerant from that liquid line, and it's going to go through a heat exchanger, which some people refer to as an economizer. It's going to flash it into a gas, and it's going to come back to the compressor. It's injected directly into the scrolls. What that injection does is it increases your mass flow, and it prevents the scrolls from overcompressing, and it allows the scrolls to use the entire scroll to actually move more mass flow into the condenser to get more heating capacity out of that. There is a power increase in that as well, but the capacity increase that you get outweighs what that power consumption is, and it greatly helps with the efficiency of that system. You can get anywhere from 10 to 25% efficiency increase by going with a vapor injection offering versus a non-injection compressor. What wet injection is, it's a mixture of gas and liquid going to the compressor. That's typically used for more extreme high compression ratio conditions, so low evap temperatures, which correlates with very low ambient temperatures, and high condensing temperatures, which typically correlates with higher supply air, or more typically higher supply water temperatures at that point. Liquid injection is another option. One of the benefits of liquid injection is it's simple to use. You don't need the economizer. You don't need, which is the heat exchanger. But some of the downfalls of that is you don't get the extra capacity out of that using liquid injection, because you're not adding that vapor to the scrolls to get that increased mass flow at that point. But it does a good job at cooling and allowing you to operate at those extreme high compression ratio conditions, and it's a little bit more of a simpler offering as well. I'll have a slide coming up to go over those differences as well. So here's a little bit more details on vapor injection. The bottom left, you can see, the top end of the compressor. So what we're doing is, we have a port right here on the compressor, just above the terminal box. And that port is coming around, and it's actually dumping in vapor into the scrolls to keep them cool. And that will drastically increase your capacity because you're bringing in more vapor to compress that will push out into that condenser as well. And like I said, it increases your efficiency quite a bit as well, because that increase in capacity, it may be 40% increase in capacity, but your power is only going up 25%, and you're going to get that 15% increase in efficiency due to that difference in power and capacity. This definitely, like I said, increases that operating envelope that you would use for hot air or hot water conditions at low ambient conditions. And right now, this is kind of the basic operating envelope for a compressor. Like I said, the x-axis, you have your saturated suction or evaporator temperature. Vertical axis, you have your condensing temperature, saturated discharge, typical cooling conditions, kind of more low compression ratio conditions. Then we have your typical heating conditions up in the left. Typically, the compressor is more efficient at low compression ratio conditions versus high compression ratio conditions. It's the compressor itself is doing more work, and then also the heat that it's generating causes that efficiency to go down as well at the high compression ratio conditions. But that's why, vapor and wet injection, helps quite a bit in these applications where you're really operating up in the top left side of the envelope itself. And, approach temperatures, coils, pumps, how much water or air you're moving through the system has a big impact on what, a specific temperatures you're going to need to operate at. It also has a big effect on how much hot water can you actually get out of the system. Can you make 140-degree hot water, to replace most condensing boilers, or some extreme conditions where you're replacing some older boilers that may go up to 150 or 160-degree hot water. A lot of that has to do with what type of coil, what type of system design you're using. This is really reiterating. This is the typical variable speed envelope. You can see this is R410A, like we said earlier. You can see hot air applications. Really, this envelope can do pretty well for anytime you want to make hot air. Really heat pump systems. You don't get the extra efficiency or capacity out of just a variable speed non-injection compressor, but you'll still be able to operate there. Where you're going to struggle with is more of the hot water applications. As you can see, a good part of that application is outside the envelope, and then you're also going to start losing capacity as you move up in that upper left side of the envelope as well, which is why the injection helps quite a bit there. There is vapor injection variable speed offerings. It's more of a new design approach that we're targeting now, and I think other OEMs are customer manufacturers are targeting it as well. It gives you the benefit of being able to overspeed, then also get that extra capacity by injecting vapor or liquid into the scrolls to help that with cooling that temperature as well. And then, a lot of these applications, they may be dual purpose. Some may be just making hot water, some may be making chilled water and hot water, depending on the season, or chilled water and hot air. So variable speed allows you to have more flexibility in having one compressor that can optimize for cooling and optimize for heating design based on whatever loads that system requires. Then here's the same envelope with the same conditions. As you can see, the hot water applications will fit inside that envelope whenever you have vapor and wet and liquid injection in here as well. This is another 410A example. It's a high pressure refrigerant. The R454B and R32 future options, which have the low global warming potential requirements, for 2024 and 2025 coming up, we'll be able to have a similar envelope as well. There is work to go below -20 degrees evap temperature, saturated suction, which would allow you to operate at these conditions at lower ambient temperatures as well.
Otto, I got a couple questions that pertain. So first is vapor injection needed at part load for VFD compressors?
Yes, if you're operating up in this region, it still is needed. So I'm going to go back to that. I'm going to go back to that first slide here to answer that question. So generally, I don't know if you can see the colors very well, but this purple envelope right here, if it's inside this envelope, typically you don't need vapor injection. You won't get the extra capacity for heating, but you just won't need it. You start getting into vapor injection in between this purple and green area right here, then you start getting into wet and liquid injection requirements as you go above that green area. This is just more of a generic envelope. Envelopes are specific to the specific compressor, but it's typically, the higher compression ratio you go is when you start needing vapor injection, and then when you start needing the wet injection, which is a vapor and liquid mix.
All right, great, thanks. One other question is, can you explain how the economizer works, which flashes the gas?
Yep, I have a couple slides a little bit later that's going to show that. in detail. It shows the system, it shows where the economizer is and the valves that are needed for that. Was that all the questions for now, Ryan? I can probably answer that second one here coming up a little bit.
Yes, that's it for now.
Okay. Yeah, then kind of the final envelope that I'm going to show. This is a low pressure refrigerant, so R134A. In the future, it might be an R513A type of system because that's got the low global warming potential as well. But as you can see, there's limitations on what that evap temperature is for saturated suction. So a lot of these systems require a higher evap temperature. So it can be a ground loop system or something similar to that in order to keep that evap temperature high in order to make very hot water. So these aren't as common systems as what replacing more boiler applications are for Europe, but they're still widely used, especially if there's some type of a lake or ground source in order to keep that evap temperature up. And I'm going to jump here. This is going to answer some of that vapor injection questions, I believe. This is an example of a single compressor with vapor injection in the system. In today's systems, your typical system, you're going to have your compressor, your condenser, your evaporator, and your expansion valve. When you start adding in vapor or wet injection, you are going to add you're going to add an extra heat exchanger, which is also known as an economizer to that. So you're going to come off that liquid line, and there's going to be a solenoid valve, typically, which you can open or shut in order to isolate the main system from the injection side of the system. That's going to go through typically an electronic expansion valve because it's going to have to be able to open and shut, more to a wide variety of mass flows. Typically, we're trying to control that, 7 to 10 degrees superheat for vapor injection. That's going to go through a heat exchanger to help make sure that that gas flashes when it goes back into the scroll itself. And that's where you start getting your drastic increase in capacity because you're bringing this extra vapor, and it's warmer vapor than what it would be if it would go all the way through the evaporator and cool down from the outside. So you're increasing that mass flow. The compressor's built-in volume ratio at that point is getting larger, which allows you to move more refrigerant into the condenser in order to get more heating capacity. I'm going to be showing a Tandem coming up here in a little bit, but the OEM for the system, they would be installing, this lines within their system in order to get that extra capacity out of that condenser that they would need. Here's a little bit more detailed. We have Tandem offerings as well. So it's doing the exact same thing, except you're doubling the compressors. You have 2 expansion valves in there, and the solenoid valves are closer to the compressor, so you can isolate them better as well. There's a controller that they can use. It can be, a OEM, compressor controller, or it can be the system controller. Can have that logic in there as well. But what this is doing is it's monitoring the temperature of the scrolls itself, and it's determining, okay, this is how much vapor we need to bring back to those compressors by controlling the superheat to keep that discharge temperature cool. And then also, whenever it moves the wet injection, it does the same thing. It controls how much wet injection is brought back to the compressor, which is a mixture of vapor and liquid, which needs a lower superheat value than what that 7 to 10 degrees typically would with just vapor injection itself. This is going to communicate with the main controller in the system as well. So as you can see, it's a little bit more complicated system than what you typically would see in your standard, DX type of system. But these lines are relatively small. They're not moving the same mass flow that you're moving around, the entire system. But the size of those lines obviously depends on, the size of the system and compressors itself as well. And here's an example of liquid injection. So, as I said earlier, it's a little bit more of a simple system. So you don't have the economizer or heat exchanger. You don't have the expansion valve on that line. All you have is fluid coming from that liquid line, coming back to the compressor itself. And then there's a controller typically built onto the compressor, which is going to control how much liquid injection is needed in that compressor in order to keep it cool. And there's usually a discharge sensor required as well on the system. Like I said, it's a simple system, so a lot of times, that's a quick and easy system to get out in the market, but you don't get that extra capacity with liquid injection because you're not bringing that vapor back to the compressor to get compressed and move more mass flow out to the condenser at that point. So you're losing capacity, you're a little bit less efficient as well, but it's kind of a quick, simple approach to it as well.
Otto, I got a couple more questions.
Yeah.
One is, what is the highest temperature hot water that a compressor can generate fairly efficiently? That's a general one. You could leave to the end if you want.
Yeah, I think a lot of that depends on what they mean by fairly efficient. Hot water, like I said earlier, though, a lot of it depends on the system itself and what your outside temperature is. If your outside temperature is 10 degrees, most OEMs can probably make 150-degree hot water out of 10-degree ambient temperature, because that's going to operate typically in 0 degrees evap, 150 condensing. And if you have vapor injection on there, that drastically helps what your efficiency of that system is going to be. But if it's real cold outside, negative 10 degrees, and you're still wanting to make 150-degree hot water, you're not typically going to be able to do that with compressor technology. You may be able to get 135 or 140, but typically you're going to have limitations as you go colder on the outside air temperature, based on what the hot water condition is. Which the downfall is that's kind of the opposite you want. A lot of times if it's colder outside, you may want a little bit warmer, a little bit hotter hot water at that point. But there's limitations based on what that high compression ratio condition is and what that high discharge temperature leads to.
All right, great. Next is a de-superheating valve needed?
No, really all you need is a solenoid valve to shut it off, and then an electronic expansion valve. You still need your main expansion valve in there, but we don't need a de-superheating valve in the system.
Okay. Then regarding mass flow, the question is, what is the typical percent mass flow and what controls the vapor injection mass flow?
Okay. So what's really controlling that mass flow is the controller. It can be the system controller, it can be our controller. And what that controller is trying to do is really control what that discharge temperature of the compressors are. So it's actually controlling what the superheat going to those compressors are doing. So the more cooling that's needed in the scrolls, typically the more mass flow you're going to get. And typically the more heating you need in the scrolls is the upper left side of the envelope, where you would want some of that additional capacity as well. So as you go farther and farther up on the left side of the envelope, you keep getting more and more capacity benefit for vapor injection than versus a non-injection compressor.
I think that's it.
Okay. Yeah, I guess, like I said, though, this is a new technology for North America. There's been OEMs that's used it, but it hasn't been in wide use, just simply because, a lot of places, especially in the United States, natural gas has been cheap. There hasn't been much of a demand for, forcing electrification in the systems. So a lot of times for the end user, it's been, cheaper and simpler to use natural gas and possibly even propane for heating equipment. But as we move forward, this technology is going to come fast to North America, and we're going to see a drastic increase in need for heating with compression technology. And one more benefit, I guess, to the vapor and wet injection other than just the extended envelope would be, the increased efficiency and increased capacity kind of helps offset some of the cost of the, the extra solenoid valve, extra heat exchanger, and expansion valve and the piping to go back to the compressor, because you can use smaller compressors to get more capacity due to that injection into the compressor itself and the increased mass flow. Yeah, I guess, Ryan, that's all I had for the presentation. I don't know if there's more questions. And
I do have a couple more, and people can type them as they need. First is, does the liquid injection not slug the compressor a little?
it shouldn't, because it's small amount of liquid that they're dropping in there at that point. So it's not a reliability concern, and it's controlled by the compressor controls itself. So the compressor kind of owns how much liquid's coming in to the compressor at that point. So there's some liquid in there, but it's not enough liquid to push the oil off of the scrolls and cause lubrication issues.
Okay, great. And what alternate refrigerants are you looking at to replace 410A when it is phased out in 2024?
Yep, it's really two refrigerants. It's R454B and R32.
Okay.
And that's a similar approach to what Europe's doing today as well.
Then this one's a little general. What typical COP increase do you see when you have vapor injection?
A lot of it's going to depend on the specific operating condition. As you move farther up in the left side of the envelope, you're going to get 20% increase. If you don't get in those low evap and high condensing temperatures, you might see a 10-15% increase. It really depends on where you're taking that COP reading at.
Okay. What insulation type do you recommend for the piping of these systems?
I would leave that up to the OEM manufacturer on that one.
Yeah, we have a presentation coming up about design of these systems, so I think we'll answer that question. Then I have, is vapor injection for scroll compressor only? How about reciprocating compressor and centrifugal compressors?
I know they are used for screw compressors today. Centrifugal compressors would be an option as well. I'm not sure on reciprocating on if they're used today or not.
Okay, great. Next I have, with those refrigerants, with the 410A phase outs, do you guys have any performance on these comparatively?
We do. We share that with the OEM. The compressor performance may not be reflective of what the OEM's actually seeing though, because 454B and R32, they're going to have different heat transfer properties from each other and from what R410A has. So typically we're seeing increased efficiency in 454B and R32 with the compressor itself, but the main efficiency difference is really going to be system related. So I'll give you an example. Typically if you're trying to make 55-degree hot air, some OEMs may require an evap temperature or saturated suction temperature of 48 degrees. Well, one option that they have, they can change what their evap coil is doing at that point, or sometimes that new refrigerant may have better heat transfer properties. Well, where instead of operating at 48 degrees evaporating temperature in order to make 55 degree supply air, they may be able to bump that up to 49 or 50 degree evap temperature to make that same cooled air at that point. And that has a drastic increase in what the efficiency of the compressor in the system would be, because you're lowering the compression ratio of the compressor at that point. So it's doing less work and it's getting more efficient, and you're getting the same amount of supply air temperature as well. But that question is really going to be needed to come from the specific OEMs on their systems and how they're applying these compressors.
I think that's all the questions that we have. I'm seeing the list of questions. If I missed anyone, shoot me a note. Otherwise, thank you so much, I think that was really informative. Really appreciate you joining.
Thanks, Ryan, and thanks everyone for the
Okay, great.
time and questions as well.
Thanks. Okay, so our next presentation is scheduled for 11, so we'll give everyone a little time between now and then to get a little work done, and we'll be back at 11 o'clock. But don't leave, just stay on and mute.